Hello everyone, welcome to this video. So we are going to be solving the problem of the day again. Let's take a look at today's problem. Well, today we have got k sum parts. The problem is saying, given a binary tree and an integer k, find the number of paths in the tree which have their sum equals to k. Okay, a path may start from any node and end at any node in the downward direction. All right, and the answers could be very large, so we have to keep it in the modulo of 10 to the power 9 plus 7. Okay, the question is pretty simple. And is it demanding anything else? We just need to complete this function. We are given root and k. That is our just root and the target value. Let me just return the numbers. Yep. And we have to return an integer. So let's try to understand this problem with the help of the examples. So this is the first sample test case. Let's try to do it. Well, we have a very small tree here. It is just 1, 2, and 3. What do we have to do? We have to count the number of paths. Now, what is a path? A path could be between any two nodes. This time, there is no restriction that the path would be beginning from root or ending at leaves. The question is itself saying that a path could start from any node and end at any node. Just there is only one restriction, that the path is going to grow downwards. Fine. So if you take up any bigger tree, let's say this one, something like this. So a path could be anything. A path could be this, a path could be this, a path could be this one. Just it should grow downwards and it can start at any node and at any node. Fine. So we know what a path is. What paths do we need to count? The paths of which the sum is equal to the target. What is the target value? K is given as the target value here. So we are given k equals to 3, and this is our tree. This is our tree here. We need to calculate the paths which are actually summing up to 3. So if I say, is this path summing up to 3? Yes. 1 plus 2 equals 3. We got one path. Okay. So 1 is this one. Can we find any other one? Well, 3 is kept here, right? 3 is kept here. And one single node can also be the starting and the ending node. So the path will be itself, correct? So we can say, yes, this can also count up to 3. So the count is increased as well at this condition as well. Eventually, we have 2 paths. Thus, the output is 2, right? Still, it might be not much clear. Let's take a bigger tree with more paths so that you can understand it even better. All right, let's take a look at this tree, this beginning from here. As you can see, this time we are given 5 as the target. What do we have to do? We need to find out the paths. So if now let's go in a pre-order manner so that it is more systematic. Once we begin from here, obviously 1 is not equal to 5. We cannot count it as a path. We'll grow. I'll go here. I'll say 3. The sum will be 4, right? So obviously 4 is still not 5. The path won't be considered. Now I will go here at 2. This time the total count will be 4 plus 2, 6. But if we just count 3 and 4, because it could start from any node and end at any node. 3 plus 5, we found one path, correct? We found 3 plus 2, that is 5. So this is our first path that we can count. Done. Now, backtracking to 3, we are going to grow this side. That means we are going to go here. So calculating this one, including 3 and including this one, we can say this is also a path. 3 plus 1 plus 1. Firstly, we got 3 plus 2, then we got 1 plus 3 plus 1, right? Then once this is done, and we are to proceed, how can we proceed in this manner? You already have this here. But if you see clearly, if I again begin from this 3 and go here till this last one, I can get one more path, which is 3 plus 1 plus 1, right? We have received 3 paths so far. Let's see if we can get more. Now if I have to go here, 1 minus 1 not equals to 5, but 1 minus 1 plus 5. This path is equals to 5. We can calculate this. So I'm saying 1 minus 1 plus 5, right? Okay. Once this is done, and we go on the left side of this minus 1, we can see this path, right? We can see this path. It is 1 minus 1 plus 4 plus 1. This is also 5. And if we just take this 4 plus 1 path, it is what? It is your 5 as well, right? Now, there is one more path left. If we consider this minus 1, 4 and 2, this will also lead us to 5. It is minus 1 plus 4 and plus 2, right? And obviously, we have this 5. So again, the same condition that happened with 3. If we start from 5 and end at 5, that is also a path. This 5 will also be considered, right? So how many total paths do we have now? These are 1, 2, 3, 4, 5, 6, 7, and 8, right? So we have 8 as the answer. So now I hope it is clear what are we looking for and how are we going to approach this question. We are going to be using a pre-order traversal, okay? Now, this question can be approached in like a couple of ways. We are going to discuss them all. But a smarter way of doing this question is to at least keep the track of the paths that we are taking up here. Well, two primary approaches that we'll be discussing in this video is, first of all, keeping the track of path and calculating according to the path, right? That approach will actually end up being of O(n) square. How? We are going to see. The better approach could be, instead of keeping a track of path and calculating, we can maintain a hash map and we can simultaneously do the calculations. But we'll be keeping the track of gains this time, not the path. That solution would land up on O(n). Let's take a look at both of the approaches. First of all, let me discuss the first approach of O(n) square. What will happen in this one? Let me take a sample tree. Let's take this tree as a sample tree. Now, the target for it that I would take is, let's say, 5. We are talking about this approach. We have to keep the track of the path that we are taking. Okay, and what data structures can we use for that? We can use a vector or we can use a string, right? Or we can just typecast that later if we are having it of characters, or we can directly go for vector. Fine. Now, what we do is we start from here. We start from 3. We try to include 3 in our path, right? Now we move to 2. We move to 2. We are here. This is the string formed. Actually, we also consider one value, but just for the sake of explanation, let me start with a vector consisting of at least 2 values. So we have 3, 2 till here, right? Now what do we have to do here? We have to check for the sum. How can we check it? Yeah, we can just calculate it from here. That means we are beginning from the root, we are ending up till the path. But that is not necessary because we know the condition. Beginning and ending point of the path could be any node, not just root and the leaf. What can we do here? We can start from the end, because when we are traveling, we are changing up the endpoints, right? We are changing up the corners. It is up to us how up we are going. So assume we are at this one, we can track it till 2, or we can track it till 3, or even like it was a bigger tree, we could have tracked it till any point. So we are beginning from a certain point, that is our current call, and we can go up to calculate the sum from the end. Okay, so we'll take 2, we will add 3 to it. We got 5. The moment we got 5, we will make a universal counter, okay, the global variable counter, and we will increase it by 1 the moment we encounter any sum equals to the target value. Done. Now what will we do? We will go here. We will go to this 5 following the regular pre-order. Then once we are here at 5, the path that we are storing will be looking something like this, right? Here. This is the path. Now what do we have to do here? We have to start calculating the summation again from the end till the top. Now, what will we do? We'll add 5. We'll check that is it equal to the target. The moment we find 5 equals to 5, that means we are going to increase the counter again, right? These calls still here are done. Now what do? We need to backtrack. And the moment we backtrack, we actually need to remove the element that we have added in the path because we are keeping track of the path here. That means we go back to 2. We are again ending up at path 3, 2. We need to just pop back this 5. Once that is done, I'll go here. That means my new path would be looking something like 3, 2, 1. Right? I'll take 1. 1 plus 2, it'll be 3. 3 plus 3, it'll be 6. We did not find 5 at any place. That means we are not going to touch the counter. We'll backtrack. We'll be here. All the work of 2 is done. We'll backtrack once more. The path will be this 3 just, and then we'll move to the right side. Here, once we are going on the right side, what will we do? This 2 will be added. That means I will take 3, 2 again. Again, the calculation starts. I will say 2 plus 3. This will end up becoming 5. I will increase my counter. I will go on to the left side. It is 1 written here. 3, 2, 1 now. That means 1 plus 2, 3, 3 plus 3, 6. No 5 encountered. We are not going to touch the counter. Again, moving ahead. Now, what is happening? 3, 2, 1, 2. Right? This is the path. Starting from the end, 2 plus 1 plus 2. What do we get? 2 plus 1, 3. 3 plus 2, 5. We are having 5 here. Counter will be increased. Okay. Now, again, we'll backtrack here. We'll backtrack here because we do not have any other option here. Till here, it was 3, 2, right? And this is a new value, minus 2. So I'll do 3, 2, minus 2, right? Minus 2, 2, it will be 0. And plus 3, it will be plus 3. You're not encountering any 5. That means you're not going to increase the counter. Eventually, the answer that we'll have is 4. Right? And this is the number of paths that we are having, which are actually summing up to 5. Right? 3, 2, 5 itself, 3, 2 here, and this 3, 2, 1, 2. Okay? So I hope this approach is clear. But why we are saying that this can take up to O(n) squared? Why? Because we are traveling the tree, right? That means we are going to go to every node, right? But in the worst case scenario, the tree could be skewed completely. And then what do we have to do? We have to actually calculate it like this, right? We'll be calculating it like this. This one, then this one, then this one, and this one. It'll be storing every vector, every element in the vector. And then for every vector, what are we doing? We are calculating the sum. We went to the first one, we calculated the sum. We went to the second one, we went back. We came to the third, we went back. We came to the fourth, we went back. So what are we doing? So because we are traveling back every time till the end, we can say broadly that it is taking up n squared, right? How can we avoid this? How can we avoid this? Although for every average case, this solution works perfectly. No problem in that. But let's try to look for even optimized approach. Now this time, instead of maintaining a vector and keeping the track of the path, what I would do is I would keep a track of the gains that we are making while moving in the pre-order manner and while encountering every new node. What will we do? So I will just create up a hash map instead of a vector this time. And we'll be keeping the track of gains instead of keeping the track of path. Now I will just add up 0 and 1. Primarily, you'll get to know later. You'll realize it, why we are storing it. Now, the thing is, assume we are here at 3. We are here at 3. The summation will be 3 itself, right? The current sum that we have till here will be 3. What is our target? what is our target? Target is actually 5. We have to perform this. Current sum minus the target. What do we get? We get -2. We'll check, do we have -2 already present in the hash map? Well, currently it is not. So in this condition, what are we going to do? We are simply going to take a current sum, which is 3, and I'm going to put 1 corresponding to it. Fine. Okay, this done. Now moving to this 2. We are here. The current sum will now become 3 plus 2, that is 5. And now we have to do this 5, the current sum, minus the target. It will be equal to 0. Just for encountering this condition, we had this, right? If this is the condition, that means we are actually having the difference to be 0. We already have 1 as a value for it. So whatsoever corresponding value that we have here, corresponding to the key, we are having 1 here. We are going to add this value to our main counter. Again, you will be keeping a track of your counter. It will be a global variable. So what you will do is you will just add up 1 this time. Correct? So once we have successfully increased the counter, we have to do one more thing. We have to make a new entry here in the hash map. That will be with the current sum. The current sum is 5 here, and the value corresponding to it is 1 because we are encountering it for the first time in this iteration. Now once this is done, we are here at 5, right? A new entry. Current sum is 5, like sum till here is 5. We'll add up 5. The new current sum will become 10. Correct? Now what do I have to do? I have to do 10 minus the target. What is the target? 5. We end up getting 5. We have to find this value in the hash map. Do we have this value? Yes, we have this value. What will we do? We will add up this one here in the counter. Okay. This one is representing the path that we have gotten till here. This one is representing the path that we have gotten till here. This is this path. What we are doing, we are actually making the gains. Initially, we were at 0, correct? Initially, we were at 0. Then at a point, where did we go? We went here, 3, right? 0 added up. Then 2 added up, we went here. It became 5, right? Then 5 added up, then it became 10. We are just subtracting the target from it. We are just subtracting the target from it, and we are seeing if the value is already available. We are taking up that path. That means a path has been made till here. Okay, we are calculating this one. We are subtracting this. If this is equal to the target, we will end up getting a path here. Okay. Now let's proceed on the right side. Okay, there is a catch here. Once you're backtracking, that means you are leaving 5 here. See, you are not keeping the track of it, right? You do not have to, you are not just moving ahead in that path. You're not keeping track of that gains. You're coming back to 2, and then you'll be keeping up the tracks. You will be keeping up the gains. So for that, what you have to do is, you have to decrease this value, right? You have to put -1 to this key. Okay, this time it will be 0 now. Or you can also delete this entry. That wouldn't make any difference. Now again, we are going to go to this 2. That means we are taking up the next path. This time, the current sum till here is 5. Remember that. 5 plus 1 will be 6. 6 minus 5, it will be 1. Do we have 1 here? We do not have 1 here. That means we are not going to make a count, but we are going to make one entry. That is going to be 1 corresponding to 1. Because 1, we are just initializing it because a single path is still there, right? What is the condition? Okay, let me just mark it. Let me see if this condition is going to come here or not. The thing is, if you are at a condition that whatsoever value you are trying to enter is already present in the hash map in the form of a key, what you will do, you will increase it. If you do not have that already, you will put that value with 1. Now, once you are here, we have done it. Okay, we did not get any path here. This time we are going to backtrack. That means we can -1 it, and we will end up here, 5. All the things are done. We will backtrack, 3 here. This time we are going to go here on the other side. Again, it will be 3 plus 2, 5. What will we do? 5 minus 5. 5 minus 5. That means 0. We have 0 here. we'll increase it with a corresponding value plus 1. Now we take up this part, 5 plus 1, 6. 6 minus 5 end up being 1. Do we have 1 here? We do have 1 here. But the corresponding value here is 0. We are going to add up 0 because we have already found this path and this is no path, right? This is just a record that we have kept and it does not make any gain. Now what do? We are here. We're going to go further. It will be 5 plus 1, 6 plus 2, 8. We're going to do 8 minus 5. That means we get 3. Do we have 3 in the hash map? Yes, we have 3 in the hash map. What can we do? We can add the corresponding value 1 to it, right? What do we actually mean by that again? Let me quote it. Okay, see. First step 3, second step 2, one more step 1, one more step 2. Total part till here is 8. The target that we have is 5. If we subtract 5, that means if we subtract this, okay, the last value left is 3. If this value is present in the hash map, if we have encountered this, that means this is a valid path and we are just counting it up. Okay, fine. This is done till here. Now what do? We're going to backtrack. We're going to backtrack here. Now at this point, 5 is here. 5 minus 2. 5 minus 2, this will be 3. And 3 minus 5, this will be your minus 2. Do we have any entry for minus 2? We do not. We don't have any entry for minus 2. What will we do? We'll create an entry. Just the code will do, which actually is not going to be of any use, and the counter won't be changing. Fine. Again, eventually the traversal is done. Okay, what is the answer that we are getting? Again, we are getting 4 as the answer. 4 paths. What are the paths? Let me retrace it. This 3, 2, this 3, 2, this 2, 1, 2, and then this 5 itself. We have the 4 paths with us, correct? Okay, now let's again quickly discuss what was the flow of the recursive function that we were making. First of all, we need to calculate the current sum. So that means whatsoever sum we are getting till here, we need to add up the roots data to it to make the current sum. Then we will do sum minus the target. So the sum we have created, we need to minus target from it. We need to look that in a hash map. If that is present in our hash map, we need to increase our total with the value corresponding to it. Else, what do we have to do? We have to either make a new key if that is not already present. If that is already present, we need to increase the value of the key by 1. Okay. Now, once this is done, this is the main logic. We will call upon the subtrees. Okay. And all the things will be done by the recursion. Then once this is done, because we do have to unmake the things, we are backtracking. We need to reduce the value at sum. That means we need to reduce the corresponding value to the current sum's key. We have to do -1 there. Fine. So I hope you have understood the flow. Let's take a look at the code. So I have done my implementation in Python. You can use any language of your choice. So what I've done here is I've made this global variable total, which would be keeping the count. And then what I'm doing here is initially total is equals to 0. I'm creating one hash map in which I'm giving 0 plus 1 as the value, as the default value, because this is a condition if we are including the root in the path. If the difference of the current sum and the target is getting 0, this is just a corner case that we have to deal. Then what do we have to do? We are making up a call to the function find path sum. We are here at find path sum. We have to check if the root, if the node, which I'm representing as current here, a little confusing. If that is none, I'll simply return. If that is not, again, this is the main flow. I will create up the current sum, and that is represented by s variable here. I will do s minus target. I'm looking that thing in my hash map. If the value is found, I'll just increase my total, my global count with it. If that is not the case, what do we have to do? We have to either, okay, let me tell you the functionality of get. What happens with get is, if I'm giving s comma 0, if s is already present, it will give the corresponding value, or if s as a key is not present in your hash map, it will give 0. So it is covering up the else condition that we have discussed here. Okay, it will make a new key. If the key is not already present, the value by default will be 0. And if the key is already there, it will give the value. And in both the cases, what are we doing? We are adding 1 to it. So either it will be any new key which will correspond to 1, or any old key which will correspond to its own value plus 1. Okay, this is what will be happening here. After that, I've made up the calls to the left subtree and the right subtree. Once that is done, this is backtracking a step, and this is very crucial. We need to -1 the choice that we have made. The number that we have added, the gain that we have shown here, we need to subtract that. Once that is done, simply return it, and eventually in the main, once the functionality of this function is completely over, the total will be having the count that is required. We need to just return that total. Okay, let's try to test this code against all test cases. Okay, so here is the same code. Let's try to compile and run it. Okay, it is giving us the desired output. Let's try to submit that. Okay, so it is passing all the test cases. Fine. Let's quickly discuss the complexity. Well, we have already seen this approach is of ON. Why? Because now we are not wasting the time of going back and calculating the sum at every path, right? In the vector approach, we were going backward. We were calculating the sum, correct? And this path, we are just looking up for the values in our hash map, which is of O1. It is going to be ON into 1, right? Which will eventually end up being ON. So I hope you understood the solution. And if you like the approach, you may comment that, and do like the video. Thank you.